This, okay. So good, here comes some Zoomers. And by the way, I wonder if I saved the status of this class. It's kind of interesting. I think I did, let's see. And maybe I didn't. Oh, I think I got the GIF in my directory here. I can find it.
Hey.
Jeez.
Have fun.
Ah, there they are. All right, I'll mute them so they don't irritate each other. I'm glad they found a place. And let's see here. Yeah, so here, we're out to week 5. And this is the status of this class. There are about 280 people that have signed up, but very few of them are doing anything. 60 people are passing. So that's what is expected. A whole lot of people come look at it, but the number of people that are actually ready to really do the projects or the quizzes or anything is not very large. So that was what I figured. That's why I can afford to have so many people in there, because I don't really have to do a lot of grading. Anyway, 3 people have already done enough to pass. Nobody has done enough to get an A in the whole course, but 3 people have done enough to get a C in the whole course. Yeah.
It was sort of like the library finance being so cheap and nickel, nobody feels bad about being weak late.
Oh, sure. I mean,
you can't harm your GPA here.
No, you can't hurt your GPA. Although someone asked me is maybe I should issue a certificate to people who win. I was thinking, I'm not a college, I'm not accredited, but Microsoft isn't accredited. Cisco isn't. You just do it. So maybe I should just declare a certificate and give it to people that win. That actually makes some sense. If anybody has any like artistic skill to make some little logo or something, that would be great. I have no such skills, but I could give you a badge of whatever it's worth, saying I can. What's that? My picture. I don't think. Hopefully, you can find something that looks better than that.
Yeah.
Well, I don't know. Well, anyway, we'll see. And I do know. Anyway, that's not a bad idea, I suppose. It's just like a Cisco or Microsoft search. It's based on nothing in particular, but maybe somebody cares. And, yeah, my trademark. Yeah. Yeah, that's good. Well, anyway, yeah, I should give away T-shirts in contest. Let's see. I think of what to do, but it's a good point because I have more and more contempt for the college system, where I really. The guy at Stanford that made the first MOOC just quit entirely from tenure position. Said, this is complete nonsense. Registration fees and signing up and college and all that. I'm just going to have MOOCs and teach millions of students at a time, totally outside the system. I'm not doing that yet, but I'm pretty rebellious. So. He put like ads on the site. If you have like 1 million viewers, you make it. I think that's what he did, but I don't know. Maybe he got a MacArthur grant or something. Anyway, I still have a day job, so that's how I get paid. But anyway, and I do get a lot of students through the college, so I'm not inclined to quit teaching at college particularly, but being open to the whole world is certainly a good thing. I'm funded by taxpayer money, so it ought to be available to everybody. Anyway, so we're down to heap overflows. And heap overflows are just another form of memory corruption, like stack overflows. You have a memory map. In fact, let's just look at a live one. If I go into my Kali Linux, which I've got here, let's see. All right. Let me SSH in. There are several people that emailed me and stuff telling me how to install the tools. And those tips work on Windows, but they don't seem to work on the Mac anymore, as far as I can tell. But anyway, SSHing in works. So let me go to 127. And there's a program here we're going to use for most of the demos here called Heap 0. And all right, when you use the heap, let me get rid of the color. You define these data structures typically. You don't have to, but it's one way to use the heap. I define a data structure that has room for 64 bytes. And then I someplace do malloc. Malloc is what allocates some room on the heap. That's the idea of the heap, is dynamically allocated storage. So if you handle data and use it briefly and then you're done with it, you don't have to keep hogging up room on the stack for it. So you allocate space with malloc and then you free it with free. Now in this program, I don't think I bothered freeing it. Just when the program ends, it'll free everything. But I did allocate 2 things on the stack, one for data and one for FP. And so let's take a look at how that looks in GDB. Heap 0. Okay, if you load a program, I might be able to do it now. Yeah, nope, I got to run one. So let's do just run. Let's see how that works. Okay. Now it crashes, but I don't really care. Info proc map. Okay. So here's the memory map of that process. So here, now this is the name of the program is Heap, but that's not the heap. This is the data structure called the heap. From 804B1000 to 6D1000, it assigns a space which is really not that large, 22,000 in hex bytes, and that's the heap. And there was a CTF one time where I had to exploit something and I put in my egg and I couldn't find it. And I looked at it and it was only like 20 kilobytes. So I just brute forced the whole thing. I put in an offset of like 500 bytes and just wrote a script that would try jumping if I had 200. It really wasn't that hard to just try all the locations. It's not really that big. Anyway, this is the heap. And the whole point of using the heap is to consume less total memory. So data that I feed into this thing is stored on the heap. And by the way, the stack is, of course, here too. If you go down, here's the stack. This is what we were overflowing before. Down here, almost always at high memory. But the heap is here in a different memory location, but just as well, it's a place where you can stick data, and data can run past its boundaries and be exploited there, just like anywhere else. So there's the heap, and there's the stack. Nothing too big about it. And by default, they're here the same size, which I think is just a decision made by running the operating system. It decides what the default size is for the heap and the stack if you don't use it too much. So the heap is a more complicated data structure than the stack. The stack is very simple. You push things on, they go on word by word, you pop them out, they come off word by word. There's no structure as far as the data is concerned. You might have a structure, like you might be popping 10 bytes of a string on there, but pushing and popping it, but the stack itself does not know it's a string, doesn't know it's null terminated, doesn't know it's a pointer. It's just a data structure where you push data on and it comes off. The heap, however, has a structure because the heap is not expected to just contain a bunch of bytes. It's expected to contain objects. You push something on it, like an array or a string or something. So there's metadata around each chunk. There's a chunk of data, and then there's metadata. There's the size of the previous chunk, the size of this chunk, a pointer to the next chunk, and a pointer to the previous chunk. The heap is a doubly linked list. You can walk the heap by starting at the first chunk and then hopping to the next one and the next one and the next one. And you can also walk it backwards from here, here, and here. That is intentional. That's how you find things on the heap, because the heap could be big and you could have 100 objects on there and you want to find a particular object and you want to find it quickly. So they make it linked. So you don't have to read through all the data. You can just go hop, 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 hop to get to it. You can also detect memory corruption this way. In Cisco routers, there is a process called check heaps, which walks the heap. It runs continuously. And if every second or so, it hops down the heap, hop, 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 hops to the end, and then hops back because it's trying to detect if something has gone wrong on the heap. And if it finds anything gone wrong, it reboots the router, throw away the packets and start over. That is intended to make the Cisco routers resilient against attack and against software and hardware defects, because Cisco routers are intended to just be unattended for years and just keep going. So every time anything bad happens, they just reboot. And even if it reboots, say every 5 minutes, your data still mostly goes through. And that's the way it's designed. Anyway, so this means we can make a simple heap. So here's a data structure. I defined this thing called name64, which is just a type of data to store on the heap. That's the first object. Here's the second object on the heap, which contains a pointer. Here's this winner function, which I'll hit if I do it right. And no winner is what it prints if I fail to make it to winner. And the main program just allocates storage on the heap for those two objects. It sets the pointer of F to point to no winner. And then it just copies argv1, the string that came in on the command line, into the first one called D without checking the size. And then it goes to execute the second one. This is a somewhat artificial example to make it very easy for us to exploit it, where the data stored on the heap is actually a pointer, which is then used to run a function. So this creates a situation that is actually quite close to a buffer overflow, where there's an EIP stored at the end that you can hit. So if we put in enough data in the first object to fill it up and run over and overwrite this object, that will be a pointer. to control execution. That's why this is here, the simplest example of a heap exploit. So let's take a look at the heap. If I start this over, let me get my, here we are. So let's run with, say, A. Okay, that's the data. I'll start this program over. Now, it said level has not been passed, so I failed. My heap is here. I should be able to look at the heap. I can do x/40x, that heap location, and I can't access it, so let's put in a breakpoint. This is usually your solution for this. So let's do disassemble main. And so here I'm allocating stuff on the heap. Here's allocating more stuff on the heap. Here's printing some kind of message. Someplace it's going to copy stuff. This looks like the string copy. This is probably where it puts my data on the heap. And so I think I want to break down here at main plus 120. That should be after this data has gone on the heap. Let's try that. Break star main plus 120 and run again up here. Okay, now if I examine the heap, which is here, I have a bunch of zeros and someplace on here, there it is. There's the A's I put in. I put in what looks like 7 or 8 A's here, and they're just sitting there on the heap. Then there's more room, enough for 64 bytes, and someplace down here is a pointer. This looks like the pointer to the no winner program, and I can verify that with disassemble no winner. That starts at 804, 84C1, and right there it is. So this is the second object that points there. So all I have to do is put in enough A's to put the winner address there to take over the heap. So let's just try a simple fuzz here. I can do it with right here in the vehicle. I can do run and do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and copy and paste. That's 10, 20, 30, 40, 50, 60, 70, 80. That should do it. Start from the beginning. Now, let's examine the heap again. And someplace, yeah, here's all my 41s. And there's 8048 down there, 484, which is kind of odd. Let's just continue and see where I end up. Yeah, I got a seg fault, which is good. I'd expect that. And if I look at the registers, I don't have AA in the registers, but I did hit a seg fault of some sort. So let's go back to the slides and see how we're going here. So this is the top green bar here is where I put the A's. Down here is the pointer I'm trying to hit. All right, so if you send 80 A's, that makes it crash. So I just need to do something more controlled. So to find it, I can send in 60 and then a non-repeating string at the end and let it give a seg fault. So let me try it now. I'm going to go outside of this. I'm going to open a second shell to make this easy. SSH, Tor, make that big. Okay, 127. In fact, I probably have these objects all ready to go. That's called H2. Looks like I do. H2, okay, H2, if I get rid of the color, H2 is what prints 70 A's and then 20 more bytes. And I remember what happened, 80 wasn't quite enough, which is, by the way, there's something really important. When I first wrote these slides on a previous version of Kali about 2 years ago, 80 bytes was enough to crash the heap. Now it takes 90. This matters. As they change the operating system, it makes different decisions about how to lay out the heap. And it matters. And it's going to hurt you on project 8X. I spent the last 2 days struggling with 8X trying to figure out what was wrong until I finally got to it. It used to be, my 8X project runs on an Ubuntu 14 server, 14.04. And it used to be that you can just develop your exploit in Kali, but you can't do that anymore. Kali is no longer the same as Ubuntu. You have to really get Ubuntu 14.04 or you will be miserable trying to develop that exploit because the layout of the heap is different and your exploits don't work. Anyway, this one here, I had to make it longer. So let me go back to here. What I tried earlier, I was surprised when this didn't work because I needed 10 more. Let's put in 3, 4, 5, 6, 7, 8, 9, 10. Now I have 90 characters. Now if I start it over and continue, now it crashes at 42, 42, 42, 40. Those B's are what ends up in EIP. So there is more room between the chunks than there was 2 years ago in an earlier version of Kali. Because the operating system is free to just choose how to lay out the heap, and apparently it updated to a later version of GCC or something, and it lays out the heap differently. So be aware of that. But now, as you can see, now I'm able to put in text that ends up in the EIP. So I just need to find out how to hit it more precisely. And I could use Python, but I don't even need to use Python for this. I can just run with that. And I can take those B's out and put in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And just continue. I don't even care about the breakpoint. I just let it crash, and it's 0, 1, 2, 3. So this is the attack string, and 0, 1, 2, 3 is what it takes to make it crash. So I can make my exploit right now. Let's do nano H demo 1. I think it's around H demo 3. Just call it that. So attack equals that. Okay, I want to get rid of all this. There. And EIP, let me make this big so you can see it. Okay. EIP equals, let's put in B, C, D, E to make sure I'm hitting it. And I see I left a 0 there. Okay. And now if I print attack, oh, yeah, attack plus EIP, the B, C, D, E should end up in the attack. So let's try that. I'm going to, what's that? I think I do need the Python header. It'd be easier if I put it in. Yeah, shebang, user, bin, env Python. That would be a little more polite. Okay, let's put that in there. And Shemode, yeah, I was thinking of different ways to do it. I could also type Python manually, but it's probably better just do it this way. Okay, so now if I do this, it prints out the stuff. So if I go to the debugger here, I can run H demo 3. And that should run this and take the result and feed it in as an argument. So if I start from the beginning and then continue, yeah, it works. I have B, C, D, E. So now I can go anywhere I want. Now all I have to do is disassemble winner. And I need this value. So all I need is that, and go back to my Python. I always copy anything that's working and keep it and make another one. This is a very good habit because very often you make a mistake and break things, and you wish you could go back a step. So here, by the way, another thing I started doing, which I didn't put in the project, is I put this here in comments. This is winner. This is another good thing to make life easier. Now I want to go there, and so I got to have it backwards, 96, 84. I have to have an X there, and 04 and 08. There, that should do it. This should win. Let's see if that works. HDemo4. If I go to here and quit, and I run HDemo4 and start from the beginning and continue, then I get level passed. So I win in the debugger. Now, here's another fun fact. The heap doesn't move when you leave the debugger the way the stack does. This is actually pretty nice. So I can go out here and run heap 0, HDemo4, and I get level passed. I don't have to start moving it by 20 and 40 and 60 and 80 bytes, all that irritating garbage that we had to do on the stack. This is why some people go so far as to say heap exploits are easier than stack exploits. Yeah. Does ASLR still affect the heap? It does. So if I was using ASLR, I would have to use return-oriented programming, where instead of trying to jump directly to the heap address, I would have to find some code that jumps to that address and run that code. A very good point. ASLR would do it. And in fact, you can see here, data is there, FP is there. This thing I think I got from some CTF. So it prints that out. And if you just run it, you can see it's not changing. So this tells you that ASLR is turned off. If ASLR was on, this would be more miserable. address space layout randomization. Very important. Thank you. And so then everything would be randomized every time, and you would have to use return-oriented programming. But you still would not have to change your exploit from the debugger to leaving the debugger, the way we've had to in the past. So one irritation is not there. So there's a targeted exploit that'll get in. And all right, this one I think is my old one. Now it's longer than 72 in the modern version of Kali. All right, so the problem with the heap is that was a particularly easy artificial example where I actually stored a pointer on the heap and then jumped to something pointed to by that pointer. Now that's handy, but often they will not be doing that. Often what they're storing on the heap is just data like network traffic or something, and they're using it, but it does not contain pointers. So what can you do with a more general heap case? And here, it's actually pretty easy because of this. Remember, the heap is a doubly linked list. So if you allocate space and it happens to be in the middle of the heap, and then you free that space, the free operation then requires two writes. It requires this forward pointer to be changed to point to the new link here, and it requires this backward pointer from the later node to point back here. So it has to do two write operations. And the write operations can both be controlled by an overflow. The address it writes to is, it's going to write something back here to an address which comes from the metadata of the third node. And if I overflow the second node, I can change the metadata of the third node. And the value it writes there is the address pointed to here, which I can also affect with an overflow. So it turns out that in a general case of a heap, if all you do is free something in the middle, that means with an overflow, you can do an arbitrary write where you control both the address written and the data. And as we know, if you can do an arbitrary write, it's very easy to turn that into arbitrary code execution, because you just have to write to something that will be later used for code execution, like the global offset table, address on the stack, the detours table, the C library hooks, the exit. We've already been here. If you can do a write, you can very easily do remote code execution from that. So that's why heap exploits are powerful, even in cases that are not as artificial as the ones I've made here. All right, and in Windows, there's the default unhandled exception pointer, which I think is now a little harder to find, but it was at one time that was always very easy to find, always in a fixed location, so you didn't have to hunt for it. All right, so that's it for the general structure, and now I just want to show you a few examples. Project 8, for example, we're going to exploit a write to a heap value. So let me bring up Project 8, which is here. Okay. All right, so the vulnerable program here is heap 1. You get the source code from me, and then you compile it, by the way, with no pi, which means not position independent code, because otherwise all the addresses would be full of zeros and irritating, and no stack protector. I don't know if you really need anything other than Z exec stack here, but it works with all those extra things. So that's heap 1, which I should have here. I do have it. So let's run heap 1 and see how it looks. It gives me a seg fault when I run it with no arguments. Let's take a look at the source code and see why. Got to spell it better. Okay, get rid of the colors. All right, so this has a structure which has priority and name, and then it has a winner function, and it has a main function that creates 3 objects on the heap, 1, 2, and 3. Then it allocates it and writes, allocates number 2 and writes, and then it copies the first argument into string 1 and the second argument into string 2. And that's it. It doesn't ever free any of them at a time I use. But I'm going to be able to exploit this with an overflow into turning it into an arbitrary write. So that's what's going on. And you see the reason why it crashed is I need to have 2 command line arguments. That's what it expects. It's going to use char argv, and down here it's going to use argv1 and argv2. And a more professional program would have told me that. But this is from a CTF. They wrote a minimal program, and they gave you the source code. So the reason why it crashed is that I didn't give it an argument. I need to give it like A and B. And now it runs, and it gives you a message. This looks like I got it from the same CTF. I don't know remember where I got these, probably Easy CTF or Pico CTF. But anyway, this is the message. It's a wrap. I didn't get the winner function. So now we do the usual thing. We can try fuzzing it. So let's start with this one. If you make the first one really long, that's 10 or 11. Let's put in a few of those. That's about 80. Then I get a seg fault. So that suggests there is some value of the first one being large that causes memory corruption, and that's suggestive. So let's get that down to a more reasonable number. I still get a seg fault. This is really simple fuzzing. I don't even have to count it or anything. I'm still getting a seg fault. Okay, there I'm not. So someplace around here, I'm getting enough. So let's try this one. That was enough. Let's just go, okay. All right, let's start with that and put it in debugger and run with that and B. And it crashes here at a segmentation fault in the middle of some deep system routine. Now, this looks, at first I was pretty upset when I saw this. This looks pretty baffling. It didn't give me the extended instruction pointer right there with the BBCC in it or anything, but this is actually good. And you can tell why if you look at the instructions. You can look at the last few instructions this way, X10I, EIP minus 10. This is a simple way to do it. This shows me the last few instructions that have been executed. And here's the current instruction pointer, and here's the operation. It's moving A into EDX. Now, if I look at my registers, it's moving A into EDX, and this is the data I put in. This is A, B, C, D, E, E, F. That's what this is. So D, E, E, F ends up in EDX. And look up here, this is FG. So it looks like I didn't quite make my exploit long enough to get complete control of EAX, but it looks to me like I do have an arbitrary write and I control both ends of it, because I think what's going on, I've made it to the end and it's doing the free that's automatically generated at the end. But I don't really care. I've got an arbitrary write and I seem to control enough parameters to win. So I just have to run it again. Let's put in some more. There, I wanted it a little bit longer. And I'll start it from the beginning, just let it crash. And now I can just look at that one instruction at the EIP, and I'll see I'm moving A into EDX. I'm a little bothered by the fact that this is AX. That troubles me a little bit, but I'm not going to worry about it too much right now. Let's do that's only moving 8 bits instead of 32. Or AX, I guess, moving 16 bits. That's probably all I need because the first two are always 0804. So I can probably still take over the machine even with only that much moving. And the only other thing that bothers me is it seems to be the same thing going in both places. So let me check my, my source here. So I debug the program. I keep going. I see, yeah, up here. Oh. It's the second parameter that controls it. I should have thought of that. Okay, so let's change my exploit a little, and let's change this into B, 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 B. And now run that. And now info registers there. Okay, the second parameter is what gets written, and this part here, which is A, B, C, D, E, F, F, G, is what writes into EDX. So I think I'm ready.
So the previous one, when over the EAX, the previous run?
Yes, the previous run, some part of this ran over EAX, but if I put more bytes here, that wouldn't happen. It's because this one was too short, I think. I don't know exactly why, but I haven't really worried about it. Now I have control of both of them with this exploit. So let's just make this in Python so I can control it better. So let's call this H2A and save that. Okay, so let's make it shebang user bin env Python. rid of the colors. Okay, so let's let attack equals quote. Okay, now it was the A, B, C, D, E. It was the last F. From this point on, the next 4 bytes are the, it's the, I think the next 4 bytes, well, let's just call them EI. I think they're target. I think they're the target, but I'm not sure. We're going to find out. 0, 1, 2, 3. And the next one is the EIP. Is, let's call it, how about 5, 6, 7, 8 there. I'm just looking for something I can easily spot in hex. And I know all the numbers are 30. 30 is 30, 31 is 31. So 5, 6, 7, 8, I can see them. So now I write ATT plus target plus a space plus EIP. That's my plan. I think this will give me a controlled write where this is the data that gets written. This is the data that gets written and that's the location, or else I got them backwards. We're going to find out. So that's H2A, Shamad plus X, H2A, H2A, and let's just run it. Okay, and now let's go back to here. And instead of running with the fixed quantity right there, we'll just run with H2A. There. Start over, it crashes. If I do X, 1I, EIP, I am, oh, good. Now it's not moving just, now it's moving 32 bits. That's what I thought. There was something about a very short B that changed its mode. Now that I put a 4 bytes in B, I don't have this nonsense. So it's putting EAX and putting it in the address pointed to by EDX. So all I need to do is look at that. EAX is 5, 6, 7, 8, and EDX is a couple of letters and then 0, 1. I'm off by 2. This is the kind of work I generally recommend rather than trying to figure it out with logic. Just get close and then do it by trial and error. So I need to adjust my exploit a little. Let's go in here. I had a couple of letters, so I think I need to delete a couple of these letters. Let's see what that does. Okay, just run it again. And then just look in the registers again. Now I got 5, 6, 7, 8 here and 0, 1, 2, 3 there. So now I'm hitting them. Now, if I look at the instruction that's happening, that is here. I'm writing the data EAX into location EDX. So the 0, 1, 2, 3 is the address of the target location, okay? And the other one is the data. So let's make sure I got those labeled correctly. 0, 1, 2, 3 is the target location, and this is the data to put in there, which is EIP. I think it's right. Now all I need to do is pick a target location and pick an address to go to. Now the target location should be pretty easy to do. I will just do obj dump. Oh, first I'll go back into the debugger and disassemble. Or I can look at the source code. Lots of ways to do it. I wonder if I can look at the source code this way. No, okay. So let's disassemble main. Okay, so here we are in main. Here we are doing a malloc. Like I say, when you look at this, ignore all that. Just look for names here you can recognize. Because I don't really care about the details of this. I just want to see what routines are called. It calls malloc. It calls malloc again. It calls string copy to put the data in. And then it calls puts to do something. That puts something on a screen. So all I have to do is hijack this puts. That would do the job. If I can change the contents of puts, I can take over the box. So that's what I want to do, is affect puts. So let's go back to here and do obj dump minus R on this program, which is heap 1, and find puts. There's puts. So that's the information I need. I'm going to put that in my file. I'm going to take my H2A and copy it to H2B, and then nano H2B. And in here, I'm just going to put useful information. That's puts, okay? Now, there's other useful information I want to put in here. I want to put in the address I'm jumping to. And that is disassemble winner. Okay, this is where winner starts. That's where I want to go. So I'm going to put that in here too as a comment. There. So now I'm ready. The target is the puts up there. So that is D4, 98, 04, 08. And let's get rid of the colors. And the data to put in that is that number. So it's A6, 84, 08, 04 that is, 08. All right. So that will take puts and change its address to the address of the winning function. That should do it. Unless I fouled it up, which is certainly possible. So that's H2B. So I quit this and I run it with H2B. Start from the beginning, and we have a winner. So that works. And again, if it works in the debugger, I expect it to work fine outside the debugger. So that would be heap 1 /H2B, and we have a winner because nothing should change from leaving the debugger. So that's good, clean fun. And yeah.
When you went to the system function, so you can't really go here and do a big function start.
Yes, that's a very good point. The question is, if you're inside a system function, you can't put a breakpoint in there, and that is correct. That's why that can be annoying. When I was having trouble with the next one I'm going to show you, P8X, I had a lot of suffering there because I was trying to compare Kali to Ubuntu, and they weren't the same. And I wanted to break and look at what I'd done to the heap, and I couldn't do it. Not very easily. That's a problem. So what I do is change my exploit to something that will crash just to get in there. Yeah, that's right. You can't break inside that system function. You can only break in your source code. Good. So that's the first two. Now I've got another couple to show you, but I'm thinking perhaps we should take a 10-minute break first. Maybe not. Let's carry on with 8X, and then I'll show you that. So 8X, actually, yeah, we'll take a 10-minute break because I need to go get a hub to connect to unfiltered internet, or I need to go get a wireless router. I have a danger zone in here, but I need to set up an unfiltered network. So let's take a break. I'm going to stop the share, and we'll pick up at 2. I'll restart it. So it gives it about 12 minutes. I'm going to run and get a wireless router, because you can't do the next one without unfiltered internet.
So this is content as a picture.
Yeah.